Hi, welcome to Lecture 8. Lecture 8 is about simple linear regression. Is in the chapter 6 of the textbook. Yes, we have 5 sections for this time. And the first is the introduction. And the last one is the summary. Mainly are the 3 is about the least squares regression, statistical inference in regression, and then use the R-squared to describe the strength of a fit. As for the instruction, mainly we're going to talk about the main ideas. The whole idea of this so-called, not only just simple linear regression, but also like in chapter 7, we're talking about the multiple linear regression. They're all about causality. But here, for example, we have 2 variables, right? Y and X. They are quantitative variables, numerical variables. And of course, they representing a population. We are very interested in explaining y in terms of x. Or put another way, as how y varies, right, with changes in x. So basically it says the changes in x cause y to change. Okay, that's the idea. That's what we mean by causality. For example, here we have y as the soybean crop yield, and the x is the amount of fertilizer. Of course, generally we say fertilizer will cause the soybean crop yield. Generally we say more fertilizer, more yield. And then another example as say y is the hourly wage, x is the years of education, right? So with more years of education, a person earns higher wage, and then x is the number of police officers, and y is the community crime rate. So this is also a very famous example, right? So usually with higher number of police officers, we would expect the community crime rate will go down. Also in chapter 1, we discussed the so-called scatter plot and the correlation coefficient to study linear relationship between x and y. When we're talking about the association between 2 numerical variables, we could use the scatter plot as the graphic tool, or use the correlation coefficient as a numeric tool to describe. And here we are one step further. We write down an equation. Okay, see, this is the first time. Like we put the y as a kind of like a function of x. So this equation 6.1 is called simple linear regression model. Okay. Y is simple because we only have 2 variables, y and x. Okay. Y is linear because you can see right here on the right hand side, this is a linear function of x. Let's talking about some kind of like terminologies. Here, x and y have several different names used interchangeably as follows here. Say we could call y as a dependent variable, x as independent variable. This exactly follows the function idea, right? In the math, we have y variable as dependent variable, x as independent variable, right? We get a input of x, and then we get output of y. And also we have another pair, say explained variable and explanatory variable. Okay, because x explains y is explained by x. Okay, and also we're talking about response variable and the control variable. This is more like in the so-called clinical trial, or in the science fields, right? They could do experiment. They could control the x and see how y is going to respond to the control of x. And we're talking about the predicted variable and the predictor variable. This one is more popular now because in the so-called big data, we always want to predict y based on what we have on x. Okay, and then also we have a regressant and a regressor. This one is not that popular. Okay, so but in our class, I would recommend the first two pairs. Okay, so yes, and we talk about the y and x, right? Y and x in the model, and also we're talking about the u. What is this u? This is so-called the error term or disturbance in the relationship. Why do we need this term? Because in the reality, it's kind of naive, right? We just say one factor unknown x is gonna cause the y. This kind of assumption is a little naive, because in the real life we have many factors gonna cause the y. That's why we single out x, and the rest we just put it as just one term as in u. Okay, that's why a simple regression analysis effectively treats all factors affecting y other than x as being unobserved, because most of the time, yes, we could not observe all of them. That's why we put them as just one term, say unobserved. That's why we use the term u. Okay, but some textbooks, they call it as so-called error term or disturbance. What does that mean? Because whatever we can come up with in x, right? This term is the one we already know, or we can get some observation about. But this u guy, since they are unobserved, we cannot get it. And that's why we could say unobserved. But the other term, you could understand this u as the difference between something we can observe, right? Y and x, the difference between these two as, say, deviations, right? See, this is something you observed about y. Y you could observe, that's what we get from the data. X we could observe also, and we assume this kind of linear structure in x. And then what's the difference of these two? Is u. Okay, that's we put as the error term. So this equation 6.1 also addresses the issues of the functional relationship between y and x. If other factors in u are held fixed, that means basically the change of u is 0, then the change of y is gonna be proportional to the change of x. And this index actually is beta 1. Actually, that's the main strength of this so-called linear regression. Why do we need to assume the linear? Because if we have this model right there, right here, and also we have this kind of assumption, say, you know, whatever this error changes up and down, but the total is gonna be 0, then the change of x and the change of y is proportional to each other. So the change of y is simply beta 1 multiplied by the change of x. This means that beta 1 is the so-called slope parameter in the relationship between y and x, holding all the factors in the epsilon fixed, right? In the u fixed. The intercept variable parameter beta naught or beta 0 is called constant term, also has its use, though it's really central to a analysis, because why is not central? Why is not central to an analysis? Because exactly right here. Because if the change of the error term is 0, then the change of y has nothing to do with beta naught, only beta 1. Okay. Assumptions for linear regression. We always make assumptions, right? Okay, the first assumption actually is the model itself, right? Okay, this is the simple linear regression model. The second assumption is about the random sampling. We have a sample, a random sample of size n. That means we have n pairs of xi and yi. I goes from 1 to n. Of course, we assume this random sample is following from the population modeled in the assumption 1. Assumption 3, some variations in the explanatory variables. That basically says for this xi, you cannot just the same value. Okay, xi should be varied, okay, instead of a constant. The fourth assumption, it says, even though we could not observe this u guy, but we gotta be careful, this u and x are uncorrelated. Okay? The conditional expectation of the u given x is 0. So basically, we say this observed part and unobserved part, they should not be correlated. Okay, so this one basically means the correlation between u and x is 0. Later we're going to use this assumption 4. Assumption 5 is about the error term. Say this error term, even though the conditional expectation is 0, that's basically say no matter what x value is, expected value of u is 0. This kind of like makes sense, right? Because we'll always assume if we observed something, right? Sometimes you observe a little bit up, sometimes you observe a little bit down. Up and downs, they cancel out each other. You end up with 0. And then also we say, this variation should be a constant also. Yes, we have sometimes up and sometimes down, right? This kind of up and downs, they are kind of, is kind of in the same degree, okay? Kind of up and downs. And the last one is about the normality. So we assume this error term is also normally distributed with the mean as 0, variance as sigma square. And here is even, say, one step further to say u is independent of explanatory variable. Okay, if we say two variables are independent, it's even stronger to say these two variables are uncorrelated, right? With these 6 assumptions, then we can do something, all right? The first part, you can see this so-called population regression function. Compared with 6.1, this is exactly, we get rid of this u term, the error term, right? How could we get rid of the error term? Because that's exactly from the assumption, say, conditional expectation of u given x is 0, right? You take this one is 0, then only this part left, okay? We did not talking about this conditional expectation idea before, but here you could just generally think kind of like an expected value of y, okay? All right? The mean of y, the average of y. So this 6.2 shows that is a linear function of x. You can see this is really a linear function of x, right? This is the linear function in the math definition. Because for the 6.1, we put as an assumption 1, right? Here is not really a linear function in terms of x because the u is in it, right? But here u is gone. The u-turn is gone. Only x turn left, right? This clearly is a linear function for x. The linearity means that a 1 unit increase in x changes the expected value of y by the amount of beta 1. Okay, that's exactly the idea here. This 6.2 tells us how the average value of y changes with x. Here, it does not say y equals beta naught plus beta 1x. Okay. So if you want to use a single value of y, you have to use the 6.1 equation, the original so-called regression model, right? We have the u-turn in it. But if we talk about the average sense, then we can ignore the u-turn. That's the difference. That's why this 6.2 is called a population regression function. We put the whole expected value of y kind of like the variable on the left-hand side. Yes, this picture I like it very much because think about each curve is bell-shaped, okay? Because you have to look at this way, okay? Right. And then for the specific value here with x1, then that's the mean. You can see there is a vertical line, right? You see this is what? This is a bell-shaped curve, is a normal. So this normal curve or bell-shaped curve use this value as its center, as its mean. What is this value? That's exactly expected value of y given x. Okay, yeah, given x1, there is an expected value of y, and this expected value of y exactly the what? The center of this bell-shaped curve. Or you can say this normal distribution use this value as its mean, right? The same thing here. The same thing here. That's why you can see right here, each value on this line, that's a mean of a normal distribution. Let's take a look at the example. This example is from the textbook. We are considering the RFT, this kind of a score to measure the so-called cognitive ability and age. So this is the y variable. This is about cognitive function. And then we're talking about another x variable as, because we want to know this cognitive function changes over time. Over time, that's about x variable is age. Okay. So from this data set, we have age as x variable, RFFT score as y. Okay. And then this is exactly the what? The scatter plot, right? Association of RFFT score with age in this data. Okay. We have how many observations in this data? 500. Okay, we plot this one. So this is exactly what we did in chapter 1. So we make a scatter plot, and then what is the relationship between y and x? In chapter 1, we could just say, okay, we could eyeball a line. This line is negatively sloped, or you can say downward sloped. Then we could say y and x have a linear, and also of course this is what? Negative linear relationship, right? That's exactly what we did in chapter 1. But what we are doing here, basically the same idea, right? Yes, we assume there is a straight line, and then here we put this straight line as the PRF, population regression function. Okay, we put the expected value of y given x, in this case is RFFT given age, as a linear function of age. Does it make sense? So compare with what we did in chapter 1, here we say, okay, there is a red line here, okay? And then we put this red line as this guy, okay? But we have to answer another question, right? We gotta be careful. Here is only like a what? Is still kind of like an assumption, right? Yeah, we do not assume this one directly, but we get this 6.2 because we have these 6 assumptions here. So we are still doing with what? Assumptions. That's equivalent to say we do not know what is this beta naught, what is this beta 1 value. Okay, we can only get the values of age, value of RF of t from the sample, from the data. Is that correct? But we do not know what's the value for beta naught and beta 1. Okay, so here you could still think this is assumption. Okay, so obviously the rest of this lecture is how can we get the values of the beta naught and the beta 1. Okay, that's the key for this lecture, I would say that. That's why we move to the second section, is so-called least squares regression. Let's just hold on for the why do we come up with this name. Later we're going to explain, okay? But right now we just want to know what we are going to do with that. So we assume this is the random sample size n from the population. How this population is described? The population is described by this model, right? You can see back to this chart. You can, okay, we say, okay, if we have y I, in this case is RFT scores, and xi are the age. So we observed the RFFT score and age for how many persons? 500 persons, right? We got 500 pairs of those x and y's. That's how we get these dots, right? Each dot it has x, it has a y. Okay, so you get so many stars, so many dots. All right, we assume this dot is from a model like this. Okay, right? From a model like this. And this model has a nice property. Why? Because the conditional expected value of RFFT given age is a linear function for age. Does it make sense? So the problem now is to obtain estimates of the intercept beta naught and slope beta 1. Can we get the estimates of these two or not? See, we translated this problem into a estimation problem in statistics. You can see, originally we are interested in what's the relationship between y and x. Now we put this relationship first as this guy, okay? And then with some assumptions, we say, okay, we can get this guy. Right? This is so-called population regression function. And here, you clearly can see that the U term is gone, and then only beta naught and beta 1 are unknown because we know the yi's, we know the xi's, okay? How are we going to do this? That's exactly I said just now, right? We have to back to the assumptions, because for assumption 4 and 6, we know the expected value of the error terms and the correlation between x and the error terms are 0. So these are what? This error term is defined from the assumption 1. And then we plug in the u in it, right? This is the u. And this is the u also. We got the expected value of u, 0, expected value of x times u is also 0, right here. And with these two equations, we could find the so-called sample counterparts. This one, I should say a little bit more about it, right? Because think about the estimation we have done so far, right? How can I estimate the mu, the population mean? We use the sample mean. See, what is the mu? Mu's expected value of x equals mu, right? What is the sample mean x bar of x? Basically, x bar is 1 over n. You sum xi's. Okay. So to get the expected value in the population sense is parallel to how you can get the sample mean in the sample sense. Okay. Because this is something we can do because we know all these xi's. To get the sample mean is very easy. You just add all of them together and then divide by n, the sample mean. But do we know this mu guy? We do not. That's why we use x bar to estimate mu. Here is the same idea. With our assumptions, we know expected value of this u guy is 0. And then what is the u in the sample sense? That's the u in the sample sense, right? Add all of the u, because we come up with estimate of the beta naught and beta 1. And then we could have a so-called discrepancy between the observed yi and assumed yi, okay? The difference is exactly what we mean by here. I put u as a hat. You could think that way. You could think that as a kind of a estimate for u, because you have to put a double quote for this estimate because we never gonna estimate the u, right? Because we only estimate the beta naught and the beta 1. But this kind of like you can mimic the situation like that. And here's the same idea. This is kind of also mu hat, right? With the hat, then you can just what? Replace the expected value in the population sense by the sample mean in the sample case, sample sense. And then we could solve these two equations, okay? You put this as 1, this as 2. And then we have two unknowns, beta 1 hat and beta naught hat. And x and y, they are observed, they are known. That's why we end up with two formulas to get the solutions to these two equations. Okay, we have beta 1 hat and then we have beta naught hat. Of course, we have to use the beta 1 hat to calculate the beta naught hat. You can see this beta 1 hat only has what? Has x and y in it. The x bar and the y bar, they're just the sample mean of the xi and the yi's. So finally, we could say this y hat equals beta naught hat plus beta 1 hat. That's y hat. What is this y hat? Y hat, you could just think of as the predicted values from the equation 6.3. They are just estimated for yi. Okay. Right. Why do we need estimate for yi? Because yi is observed, right? But if we really want to know what caused the y, then we need just come up with this y hat. Of course, this yi and the yi hat, they are not exactly the same. Okay, or the other way, you could understand it this way. Okay, this is kind of the PRF, population regression function, but we we replace this right hand side as the y hat, and the left hand side we replace with the corresponding beta naught hat and the beta 1 hat. Okay, so this is kind of like a parallel between the population and the sample, right? This is the population, this is the sample. Some of you may already guess it, right? The difference between the yi and the y hat we defined as a term called residual. Okay, and then we just replace this yi hat by this so-called SRF, sample regression function. That's how we got this ui hat. Now take a look, because we know every term on the right. So finally, we have a result for this ui hat. Because don't forget, what is the 6.1 equation, right? This is for at the very beginning. We have a ui in it. Okay, but finally, if we do whatever we have accomplished so far, we could end up with a expression for ui. Of course, we put a hat on the top. So this one is originally unobserved, but now we could have a value for it, right? So in this sense, this is a big accomplishment. That's why this residual is very important. Okay, first we just want to use a chart to denote what ui, this residual mean. Residuals mean, okay? So you can see right here x and y, and then with a blue line as the so-called estimated sample regression function, because this is mimic to the population one, parallel to the population one, okay? Right. Now, for each individual xi right here, it has observed the value of y right here, right? See, this is the yi. In this point is xi and yi. But now, with this xi value, then we could find the y hat value. Yi hat value. You can see yi hat value most of the time is not going to be the same as yi. There is discrepancy. Discrepancy is exactly the ui. And then for each pair, we should easily get what this ui is, right? See that? Yeah, please make sure you understand what the residual means here. Okay, with the residual, then we can go back to say something more about this beta naught hat and beta 1 hat. And of course, we have to use calculus, which is not required for this course. We can show that this one is to make the sum of the squared residuals the smallest. You see right here. This is exactly the what? Ui hat, right? Because yi hat equals beta naught plus beta 1 hat. Beta naught hat, beta 1 hat, and then xi. See, this is exactly the yi minus yi hat. That's exactly the what? Residual. We square the residual and then add them together. That's kind of the sum of squared residuals. Okay. A nice property of this one, if we got this beta 1 hat and beta naught hat, beta 0 hat, then these two are gonna make this sum of the squared residuals the smallest. What does this mean? Back to this example. See here, we could understand it, yes, we are gonna assume a model for this problem, right? The relationship between RF of t and age. There is a model. That's exactly the original 6.1 equation. And with the assumption we could get this PRF. But the key question is how we're gonna get the values for beta naught and beta 1. Okay, that's the key. How we're gonna get it? You could draw any line as you want. But which one is the beta 1, beta naught hat and beta 1 hat? Is the one who, I cannot use who, which has the smallest sum of the UIs. Okay, because whenever you have a line, you could use this dot. You do it one by one, okay? Get a discrepancy of that, right? This is exactly UI hat. And in our case, you should have 500 UI hats. And you square these 500 UI hats, add them together. And then you do it for every straight line as you want. Which one will be the one finally we're gonna keep is the one who make this sum of these squared UIs the smallest one we're gonna keep as the estimate for beta naught and beta 1. That's why we call this as least square, right? Remember, right? That's exactly what we mean by least square, because we make the sum of the squared residuals the smallest. Because usually we put an ordinary least square in the front, and then we simplify as OLS, okay? Of course, details of the proof is not required for this course, and we use that as a fact. You're more than welcome to take a look at the appendix. Okay, after we get the beta naught hat and the beta 1 hat, and this beta 1 hat is very interesting. It can be decomposed by two parts, because originally this one is kind of complicated, right? This way, and then we can change this one into a formula which includes the R correlation coefficient between y and x we learned in chapter 1. What is the Sx and Sy? They are the sample standard deviation of x and y. You can see right here, Sy and Sx both are positive. Then whether beta 1 hat is positive or not depends on whether this R is positive or not. So what is R positive means that relationship between y and x, or you can say association between y and x, is positive. If it's positive, then this beta 1 hat should be positive also. You can see right here, this one can be closely related to the correlation coefficient, right? Take a look. Here we clearly see this is a negative sloped. That means this beta 1 hat should be less than 0. Okay. Yes, you could just draw a line as positive, but this line is not gonna keep, right? Because you could not have this smallest what? Sum of squares, okay? Right here. So what we keep as the beta naught hat and beta 1 hat will make this squared sum. The sum of squared residuals, the smallest. Okay. Of course, this kind of calculation is complicated. That's why we use the R to do it, right? Use the lim, means linear model, okay? And then this is the y tilde x, right? And then if we put a dollar sign with the coefficient there, they're gonna tell us this guy is gonna be the beta naught hat, and this guy is gonna be the beta 1 hat. This is this one. This is the beta naught hat, and this is the beta 1 hat. So they use the R. This is just simple one line of code can give us a very nice calculation. We do not need to do this by hand, okay? Especially for a data set with 500 observations. That's gonna be crazy if we do it by hand, okay? Now let's say something about the statistical inference. Statistical inference, basically we focus on beta 1, okay, as we said, right? That's our center. In terms of the inference, right, we either do the hypothesis testing or the estimation. So we start with the hypothesis testing. We want to know, yes, x and y variables are not associated. Yes, I think it's better to use the lowercase, okay, x, y. Are not associated. That's equivalent to say this beta 1 equals 0, right? You can see why this is important. Why? Remember this one is beta naught plus beta 1x. If y has nothing to do with x, that's basically say this beta 1 has to be 0, right? If it's non-zero, then it has x in it. If we have beta 1 equals 0, you put it in, then only beta naught left. Okay, that's why we say y and x are not associated. How to do this test? We just first calculated the test statistic. Here, this is the value from sample, and this is the value we hypothesized, right? In our case is 0, okay, this number. And the standard error of the beta 1 hat, yes, if you refer to the section 4 of the textbook, it will give you the detailed formula about how to calculate it. But here I would not recommend you do it by hand, okay, because they're too complicated. But you got to know what's going on here, okay? Yes, because beta 1 naught equals 0, that means beta 1 hat minus 0, that's basically beta 1 hat, right? And this t statistics under the null hypothesis has degrees freedom of n minus 1, is a t distribution. And then for 95% confidence interval for the beta 1 is beta 1 hat, the estimate plus or minus this term as margin of the error, right? This margin of the error, that's exactly similar to what we had for the estimation of mean, remember? In our case, okay, No, here is what? The standard error. This term is what? Is the S over square root n. See this whole term as what? Margin of the error. The standard formulas for calculate this one, right? Yes, as I said, right? I would not recommend it by hand, okay? Now, the last question we want to consider here, after we got this regression 9, right? We want to make some comments. Is this a good model or not, right? We use R squared to do it. What is R squared? R squared basically say variance of the predicted value of y, the variance of yi hat, divided by variance of the y values. Okay. What is yy hat? Yy hat, no, it's not just y1, okay, it's the yi hat. You could just say this is the predicted value given xi, okay? Or you could just say is the estimated value for yi hat for the i's individual. But we already have the yi, right? We observe it. Then it has a variance also. So the ratio of these two variance, we define R squared. You should not be surprised if I say the variance of this top is smaller than the variance on the bottom, okay, most of the time. If this ratio is 1, what does that mean? That means the variance of the yi hat and the variance of yi are the same, basically. That means everything can be explained by yi hat. Everything in yi can be explained by yi hat. What is yi hat? Y hat is exactly the simple linear regression of xi, right? Because this one is none, okay? And also can be calculated as the variance of yi minus the variance of the ui hat. You can see right here, because take a look. Yi minus yi hat equals ui hat. Okay. Then yi hat equals yi minus the ui hat. And then variance of yi hat equals variance of these two. And because since they are unrelated, that's why the variance of yi minus the variance of ui hat. So basically says yi equals yi hat plus ui hat. So this part is explained, this part is unexplained. So the yi can only be explained by yi hat this big. It has a what? Discrepancy or error term. No, we cannot use that as error term. You can just say as the residual, okay? Okay, cool. And then in terms of the summary. The summary, I really want you to know what is the linear regression from the model assumptions, and then how we're gonna estimate the parameters beta naught and beta 1 by the so-called least square, or you can say OLS. And here we just do it in what? In R unknown, SR, right? We run a linear regression. We put a summary, and then here we get the estimates, and then the standard errors for beta naught hat, beta 1 hat. And then these are the standard error. And then the corresponding p-values and the t statistic value, So here we pretty much, if you use a summary of this linear regression, then you predict everything we want. That's the final one. Okay. Now finally we can see something. You can see right here, this red line is the expected value of y given x, beta naught plus beta 1 x. And what is this yellow line is the yi hat equals beta naught hat plus beta 1 hat times x. Okay, this is the PRF, this is the SRF. So most of the time we should not know this PRF. If you know the PRF, then there is no point to run the regression, right? That's what we can get, okay, from the sample. I hope this video can help you to understand this simple linear regression better. Thank you.